So let's start with just a little bit of review back from our chemistry days. So we call this unit nuclear energy. What is nuclear? Nuclear bomb, nuclear power plant. What's the nuclear part? And yeah, having to do with the nucleus. That's where that word comes from. That involves the nucleus of atoms. So what is in the nucleus of an atom? Francesca?
Protons and electrons?
No. Close. Great. Protons and neutrons. So an atom nucleus contains some protons and some neutrons. What do you know about the charge of each of those? Carter?
Protons have a positive charge.
Yep. How about neutrons?
They have negative charge. Or no charge.
No charge. So protons have a positive charge. Neutrons have no charge. So if we imagine sort of the laws of electromagnetism, what do like poles of a magnet do? They repel each other, right? You get strong magnets try and push them together, and they don't want to be pushed together. They repel each other. Electric forces, positive and negative forces, do the same. So positively charged protons inside the nucleus should repel each other, but somehow the nucleus stays intact. Okay? It's the neutrons that help sort of glue the nucleus together. If the nucleus were just protons, they would repel each other and the nucleus couldn't stay intact. So the more protons you have in your nucleus, the more neutrons you need to keep it all together. But as we get heavier and heavier elements with more protons and more neutrons, okay, elements with more than 83 protons, even extra neutrons cannot stabilize that nucleus. It's inherently unstable and could possibly decay, could break into a more stable component. And that's where this unit is focused. We also talked about isotopes back in chemistry. What is an isotope? Isotope of an element. Mom? Yeah, it's the same element, the same number of protons, but with a different number of neutrons, giving it a slightly different mass. Here are 3 isotopes of carbon: carbon 12, carbon 13, and carbon 14. And the difference between those isotopes of carbon is in the number of neutrons. Carbon 12 has 6, carbon 13 has 7 neutrons, carbon 14 has 8 neutrons. Can you guess which of those are radioactive? Which of those have unstable nuclei which could decay? Aiden? Yeah, carbon 14 and carbon 13 are unstable. They will spontaneously decay. Carbon 12 is stable. So when we say that an atom or an element is radioactive, what we mean is that its nucleus is unstable, and at some point it may become stable by emitting, ejecting certain particles or energy. And when we say something has decayed, that's what we mean. It's given off some particle, some energy to become a stable isotope. the details of radioactive decay can get quite complex, and there's lots of different types of decay and various complexities we won't get into. We'll keep it pretty basic. We're going to talk about 3 types of decay, 3 types of nuclear radiation. We'll talk about alpha, beta, and gamma. Okay. So alpha particles. Sometimes an atom will give off what we call an alpha particle. An alpha particle is basically a helium nucleus. It's the same as a helium nucleus. Find helium on your periodic table. How many protons does it have? Great. How many, what's its atomic mass?
4.
Yep. Okay. Alpha particles are relatively large compared to the other types, and they actually can be stopped fairly easily from penetrating into something. A single sheet of paper can block alpha particles from penetrating. These were named in order of their ability to penetrate. Alpha particles having the least ability to penetrate. When we are writing the symbol for an alpha particle, this is what we write. Helium 4, 2. 4 being its atomic mass, 2 being its number of protons. Sometimes an atom gives off an alpha particle, and then it becomes stable. Other times, a beta particle may be given off. A beta particle is basically just an electron. Beta particles have a greater ability to penetrate. Beta particles can be blocked by a sheet of aluminum. To symbolize a beta particle, we just write E for electron. What about the mass of an electron? What did we say? Basically nothing. So that's the 0. Okay. And its charge is -1. So some elements are radioactive and are prone to decay at certain points. You don't have this slide, but this shows the periodic table in its full form with the radioactivity of the elements color-coded. Okay. So the stable elements that have a stable isotope are in blue, which obviously is the majority of the elements are stable or have a stable isotope. The green shows some of the elements that are radioactive, but decay very slowly, in the order of millions of years. The yellow and the orange elements are less stable. Okay? They decay in hundreds or thousands of years. Half-life is in the hundreds or thousands of years. The red and purple are extremely radioactive elements, which decay very quickly, sometimes in days or even less. So as we go up the periodic table, increasing atomic mass and atomic number, we get more and more instability, more radioactive elements. So, in beta decay, we said a nucleus gives off an electron. But if you think about what's in the nucleus, are there any electrons in the nucleus? No. So the question may be, well then, how can an electron come out of the nucleus if there are no electrons there? Well, what happens is you we know there are protons and neutrons in the nucleus. And in beta decay, sometimes a neutron spontaneously changes into a proton. In order to do that, its charge goes from 0 to +1. How is that going to happen? By getting rid of a negative electron. This neutron changes into a proton. Okay. So that's where this electron comes from. It comes from the transition of a neutron into a proton. Beta particles can be stopped by a thin sheet of metal. Then finally we have gamma rays. So alpha and beta decay were emitting actual matter, particles, electrons, okay, protons and neutrons. Gamma radiation is different. Gamma radiation is just energy, no mass, no charge. It's just the emission of energy, the release of energy from an atom. Gamma rays have the greatest ability to penetrate. It takes a thick sheet of lead to stop the penetration of gamma rays. So then we look at sort of the relative penetration ability of these types of radiation, alpha particles, beta particles, gamma rays, in order of their ability to penetrate. Okay. By experiments in which you have a radioactive source, and then you can put different types of material in front of it and detect it on the other side. To detect radiation, we use an instrument called the Geiger Counter. It's a tool that helps to detect radiation. Does anybody know when scientists first started to discover radioactive elements and radiation? No? She's one of the first, yes. When was that? When was Marie Curie experiment?
The early 1900s.
What?
The early 1900s.
Early 1900s, late 1800s, yes. Right around the turn of the century is when scientists first started really working with radioactive elements, starting to understand what that meant, identifying various elements that were radioactive, finding uses for those radioactive elements. Unfortunately, not understanding the dangers of working with those radioactive elements. So you guys must have learned about Marie Curie somewhere along the way? Yes or no? No? A lot of people know her. Okay, good. Well, let's watch a little bit about her. Great example of a scientist doing work under sort of not ideal conditions. Around that time, in Poland, for example, where she was born, women were not allowed to attend university, so she had to study on her own, eventually moving to a place where she could go to school, and as you see, becoming the first woman to receive a Nobel Prize, and the first person to win multiple Nobel Prizes.
Didn't she die from radiation poisoning?
Yes, she did. So let's just watch this and you'll learn a little bit about her.
Hello, my name is Marie Curie, and I'm going to draw my blood. No, that's not I care. That's much better. I was born Maria Sklocka in Poland on 7 November 1867. I came from a very poor family and was the youngest of five. My parents were teachers, so made sure we appreciated the value of learning. My sister died of typhus when I was 8, and my mother died of tuberculosis when I was 10. But my dad made sure I stayed in school. And I turned into a top student facing a world of opportunity. At least I would have if girls were allowed to go to university in Poland in the 1800s. So my sister and I joined an illegal underground organization, a secret university which did let women in. As they say, you just have to keep calm and Curie on. I loved it there, but I knew to get a proper education I'd need to go to a proper university. So I spent years teaching and saving enough money to study in Paris. Ah, la ville lumière. I worked really hard there and earned master's degrees in both physics and maths. On the inside, I was beaming. Honest. To continue my research, I needed to find a laboratory, which is how I met Curie, who had some space we could work in. And boy, did we work. We fell in love over our passion for science and were soon married. Talk about serious chemistry. We would have 2 daughters, but that's more to do with biology and physical science. When it was discovered that certain minerals gave off mysterious rays, I decided to investigate. I called this property radioactivity. Yes, that was me. I made up that word. No biggie. One of the minerals I studied was called pitchblende. Even though it contained uranium, it seemed to have unusually high levels of radioactivity. Man, I love that word. I realized this meant it must contain another, even more radioactive element that no one had ever seen before. Pierre gave up his research to help me investigate, and together we discovered not 1, but 2 new elements, radium and polonium. Then I figured out that radium could be used to kill cancerous cells, and people got a bit carried away. Soon they were proclaiming this dangerous glowing element to have miraculous healing properties. They put it in everything from cough syrups to lipstick, alarm clocks and chocolate. It even went into children's toys. Oops. But that wasn't my fault. And Pierre and I won the Nobel Prize for Physics in 1903 for our work in radioactivity. I was the first woman to win a Nobel Prize. That is rad science. Just when we had hit the scientific big time, Pierre was hit by a horse-drawn wagon and killed instantly. I was devastated, but determined to carry on our important work. In memory of my husband, I helped set up the Radium Institute, which aimed to use radiation to help people with cancer. And guess what? I won another Nobel Prize in chemistry. That made me the first person ever to win 2 Nobel Prizes. Another first. How about that for girl power? Then World War I broke out. I used my scientific knowledge to help the troops. I raised money to build a fleet of X-ray wagons that could be taken to the battlefield and used to diagnose millions of wounded soldiers. I refused to make profit from my work, and I was soon too poor to buy the radium I needed for my research. When the public found out about this, they campaigned to make sure I could get all the radium I needed. Thanks, folks. Even the President of the United States gave me a gram of this stuff. This might not sound like much, but its value would be equivalent to about £1 million in today's money. Unfortunately, my work had exposed me to dangerous levels of radioactivity. Did this turn me into a superhero with radioactive powers? No, sadly not. It killed me. My papers are even radioactive today. Okay, so I had some tragedies in my life, but I never gave up. My work in radioactivity has helped treat millions suffering with cancer. If you study maths and physics, then who knows? Maybe you could change the world too. Subscribe to Your Life for more videos to inspire you and help unlock your potential in our world of maths and physics.
All right. So, when an element, an atom, gives off an alpha particle or a beta particle, it changes. Okay? We call that process transmutation. One element changing into another. Because what is it that determines the identity of an atom? Joey?
Number of protons.
The number of protons. So, for example, if we have uranium 92, 238, what do those numbers mean? What is the 92? Brian? It's the number of protons. Its atomic number. 238 is its atomic mass. So if uranium decays and gives off an alpha particle, it's going to change. So when we write out these problems, which is what you're going to have to do for homework, what you do is you just start by writing the original element, uranium 92, 238. You draw an arrow, and you show what is released. In this case, we are talking about alpha decay. So an alpha particle is released, a helium nucleus. So if this uranium atom is sending off this alpha particle, what happens to its atomic number? Grady?
It goes down by 2 protons.
It goes down to it. Just sent off 2 protons in this alpha particle. So its new atomic number would be what? 90. What happens to its atomic mass? Goes down? No? 4. This is the atomic mass. So it includes these 2 protons. Yeah. And its new atomic mass becomes what? Is it uranium? What is it?
Thorium.
It is thorium. How did you find it? Just look for number 90 on the periodic table. Or look at the bottom of the slide. So yeah, when uranium 238-92 goes through alpha decay and sends out an alpha particle with 2 protons and 2 neutrons, its new atomic number is 90, its new atomic mass is 234, and it's now a different element. It has transmutated. It is now thorium. What if that thorium goes through beta decay? Again, in beta decay, what is being released? A single electron. Does the electron have any mass? So what happens to the mass of thorium? Stays the same. Where did that electron come from? The neutron converted into what? So what happens to its atomic number? Goes up by 1 because it now has 1 more proton than it did before. And it becomes a new element. Proactinium. Any questions about alpha or beta decay? Okay. Again, one more example. Here we have carbon-14, another unstable isotope of carbon. Okay, it has 8 neutrons and 6 protons. If one of those neutrons gets converted into a proton during the decay and emits an electron in the process, we then have 7 protons and 7 neutrons. It turns into nitrogen-14.
So even though it's like now 91, it doesn't like affect the atomic mass at all?
No, the atomic mass stays the same. Because the neutron had a mass of 1, when it changes into a proton, it still has a mass of 1, so the mass hasn't changed. What type of decay is this? Beta decay. Releasing an electron is beta decay. All right, let's just watch a little summary of basically almost everything we talked about, and then I'll give you your homework.
It is only in the last 100 or so years that humankind has understood that the nucleus of the chemical elements is not always fixed. It can change spontaneously from one element to another. The name for this process is radioactivity. You probably already know something about the nucleus. It's much tinier than the atom. It's made of particles called protons and neutrons. There are electrons orbiting around it. And though the atoms can share or swap electrons when they bond together, the nuclei themselves never change. Right? Well, no. Certain nuclei are not stable in that way. This means they may change suddenly, spontaneously. The radioactive nucleus flings out a small particle and transforms into another element, just like that. For example, the carbon nucleus can eject a fast-moving electron and turn into a nitrogen nucleus. There are two different particles that can be emitted from radioactive nuclei, though never together. The very fast electron is known as a beta particle. If you know a little bit about electrons, you may be thinking, what was the electron doing in the nucleus in the first place? The answer is that a neutron in the nucleus spontaneously changed into a proton, which stayed behind, and an electron flew out as a beta particle. This is not what chemistry has taught us to expect. The nucleus is supposed to be stable. Neutrons don't change into protons, except sometimes they do. The other particle that emits spontaneously from an unstable nucleus is alpha. An alpha particle is 8,000 times more massive than beta, and it's a bit slower. Alpha is made from 2 protons and 2 neutrons. If we trap a lot of alpha particles together, we get helium gas. Alpha is a helium nucleus. Like the beta particle, we would not have expected a heavier nucleus to throw out helium. But again, it happens, and the nucleus becomes a new element. So, is radioactivity useful or just dangerous? Wherever you are sitting, it is quite likely that there is a device nearby which contains a source of alpha particles, a smoke detector. The source is radioactive americium. You are totally safe from these alpha particles, which cannot travel more than a few centimeters in air. Beta particles penetrate much further through materials than alpha can. Radioactive atoms are used in medicine as tracers, to show where chemicals travel in the patient. Beta particles are emitted and have enough energy to emerge from the body and be detected. There is a third type of nuclear radiation, gamma, which is not a particle at all. It is an electromagnetic wave, like microwaves or light, but it is actually 1,000 times more energetic than visible light. Gamma rays may pass right through your body. Gamma is used to zap the bacteria in fruit to increase its shelf life, or in radiotherapy to kill cancer cells. Radioactive substances get hot, and this heat can be used to generate power. This heat has been put to use in space probes and, in the past, in pacemakers for hearts. The more abruptly nuclear radiation is slowed down, the more damage it does to the atoms it hits. This is called ionization. Alpha causes the most ionization as it crashes into other atoms, and gamma the least. For humans, the most serious effect of radiation is the damage that it can cause to our DNA. Although alpha cannot penetrate your skin, if you inhale or ingest a radioactive nucleus, the health consequences can be severe. Radioactivity is both useful and deadly, but it is all around us as a background to the natural world.